Relation of physics and astronomy. What is astronomy? And then we'll try to see about astrophysics. So astronomy is one of the branch of natural science that studies about heavenly bodies or known as astronomical objects. In our universe, የተለያዩ astronomical ቦዲዎች ወይም ኦብጀክቶች አሉ። Those astronomical bodies or ኦብጀክቶችን የሚገልጽልን የሚያስረዳን በማዕከላቸው ያለውን ሪሌሽን የሚገልጽልን አስትሮኖሚ ተብሎ ይጠራል። So in the sky, like the solar system, okay, we have different solar systems, including our solar system, and its constituent. What is there in the solar system? The property of birth, life, and days of stars. How does stars born? How does stars grows? And what will be the end of the stars? What will be the days of the stars? Interstellar gas and dusts like nebula. Here we have nebula. Here we have stars, planets, okay, moon, asteroids, galaxies, different galaxies, star clusters, okay, black holes, dark matter actually. They are different matters. So galaxy and clusters of galaxies, finally the study of the universe as a whole is studied or under astronomy. It is studied or investigated under astronomy. Astrophysics ደግሞ ስለምን ያጠናል የሚለውን ስናይ is one branch of astronomy which studies about how to apply physics knowledge or the knowledge of physics in astronomical investigation to understand astronomical objects. You see, here we have astronomical objects. To understand deeply about astronomical objects, surely you have to know or you have to apply physics knowledge. In the first place, to be astronomer, one criteria is at least we should have to have a degree of physics. So physics is highly important to understand about astronomy. Here are some physics laws and principles that are highly involved in the astronomical science. And those are Newtonian law or Newton's law of motion, Newton's law of universal gravitation, and so on. Kepler's law, Doppler's effects or Doppler's law, and so on are the most common and very important laws that are applicable in astronomy. The first law is Newton's law of gravitation. Is used to describe the motion of moon or planets around sun or motion of satellites around planets. Okay, motion of planets around the sun or motion of satellites around planets is easily explained by Newtonian law or Newton's law of gravitation. It also enables astronomers to calculate astronomical distance between astronomical bodies and enable them to determine gravitational acceleration at different locations. So how do we know? You should have to apply Newton's law of gravitation, universal law of gravitation. So those laws are concepts of physics and they are very important in astronomy. The knowledge of centrifugal force from our physics knowledge greatly helps us to understand what keeps objects in orbits or around to each other. And the other law is known to be Kepler's law. It enables us to understand planetary motion. It enables us to calculate the period of planets around the sun. So this law is very, very important law. You are going to learn in units 2. This applies to planets orbiting the sun, moon orbiting planets, or artificial satellites or commercial satellites revolving around the Earth. So you can predict the period. You can predict the approximate location. You can predict the orbital velocity. You can predict the escape velocity and so on. So these concepts are explained using Newton's law and Kepler's law. And the other important law is Doppler's effect, described as the apparent change of frequency due to the relative motion between the source and the observer. Source እና ኦብዘርቨሮች በሚኖራቸው እንቅስቃሴ ምክንያት ከሶርሱ የተነሱት ዌቮች it could be lights, it could be sound waves. ሪሲቨሩ ጋር ሲደርሱ ዲቴክተሩ ጋር ሲደርሱ ቼንጅ አላቸው። ያንን አፓረንት ቼንጅ ኦፍ ፍሪኩዌንሲ ኦኬ በመጠቀም ዩኒቨርስ ኤክስፓንድ እያደረገ ነው ወይ ወይስ ዩኒቨርስ ኮንትራክት እያደረገ ነው ወይ? አንድ አስትሮኖሚካል ቦዲ is it approaching towards us or is it receding or moving away from us? With what speed is it approaching towards us? Explained by Doppler's effect. And Doppler effect is highly applicable in astronomy, okay? And Doppler effect is a concept of physics. So ፊዚክስን መማር ግዴታ ነው። አንድ ሰው አስትሮኖሚን አጠናለሁ ብሎ የሚል ከሆነ ግዴታ ነው ማለት ነው። ሶ ይህንን ነው የሚነግረን። ፋር we have seen about three laws. Newton's law, Kepler's law, and Doppler's law are the most important law that are highly applicable in physics, and those laws in physics are applicable in astronomy. Physics of electromagnetic wave and astronomy. So astronomers collect information using electromagnetic radiation. As we have seen previously, electromagnetic radiation consists all the visible and invisible light spectrums. So using electromagnetic radiation, astronomers collect information throughout the space from different objects. It could be from stars, how hot objects are. Astronomers tells us the surface of the sun using electromagnetic radiation. How the universe was formed. We have different laws. One of the basic laws like Big Bang theory or singularity and so on. They were all explained using the electromagnetic radiation. ምንድነው የሚለውን ነገር በሰፊ ያጠናው ፊዚክስ ነው። ያንን የፊዚክስ ኮንሴፕት አስትሮኖመሮች ተጠቅመው ደግሞ ከላይ የዘረዘርናቸውን የስታሮችን መወለድ፣ የኦብጀክቶችን ሙቀት፣ የውስጥ የውጭ ሰርፌሳቸውን ምናምን የሚለውን ማወቅ፣ ዩኒቨርስ እንዴት ፎርም ሆነ፣ መጨረሻውስ ምን ሊሆን ይችላል የሚለውን ነገር ሁሉ ኤክስፕሌን የሚደረገው በዚህ ነው። Astronomers use telescopes that detect different parts of electromagnetic spectrum. ኤሌክትሮማግኔቲክ ስፔክትረም እንዳልነው ቪዚብልም ኢንቪዚብልም አለ። ቪጊዮር ብለን የምንጠራቸው ቫዮሌት፣ ኢንዲጎ፣ ብሉ፣ ግሪን፣ የሎ፣ ኦሬንጅ፣ ሬድ these are visible light spectrums. And then what? These are the visible light spectrums, and then infrared, microwave, radio wave are invisible. And from violet we have ultraviolet, X-ray, gamma ray, and so on. These are energetic light spectrum, but we can see, we can't detect. These are invisible, these are invisible. The only thing are visible from violet to red. Okay, so we have telescope. Astronomers use different type of telescope. Each type of telescope can only detect one part of the electromagnetic spectrum. For example, we have a so-called optical telescope. If we use optical telescope, it uses visible light spectrum, so we can detect all the visible light spectrums. But if we have infrared telescope, the infrared telescope it gather information using infrared. Such telescope somehow closer to very hot objects like sun. But the big problem is those telescope may collect this information using infrared and X-ray or gamma ray, but we can't detect through our naked eye. So what shall we do? We have very, very smart computers. Those smart computers will detect the radiation, and those computers will change all the data to colors that can be detected by us. So this is what the false color mean, and those telescopes use false colors. Here it's data collected using infrared. Smart computers convert those information into visible colors using pseudo colors or false colors. So these are the space observatory in Toto. ከላይ ያስቀመጥኩላችሁ ይሄ ሊንክ ከናሳ የተገኘ ነው። ይሄ ኢሜጅ ኢንፍራሬድ ኮሌክት ያደረገው ኢንፎርሜሽን ነው። as I told you, infrared more of ሆት ወደሆኑ ቦዲዎች ተጠግቶ ኢንፎርሜሽን ጋዘር የሚያደርግ ነው። እነዚህን ኢንፎርሜሽኖች ደግሞ ፎልስ በሆነ ከለር ሲዶ ከለርስ ምን ይደረጋል ብለናል? ኮንቨርት ይደረጋል ብለናል። ሶ ይሄን ኮንቨርት ሲደረግ ምን ይመስላል የሚለውን ለማየት እንሞክራለን። ዲስ ኢዝ ኢሜጅ ፍሮም ኢንፍራሬድ our smart computers convert this into visible or optical, and these colors, see, it's more clear and visible to our eye. ስለዚህ ወደ ማየት የምንችለው ከለር አድርገው የቀየሯቸው ነው። ፎልስ ከለርስ እየተባሉ ይጠራሉ ማለት ነው። ኦኬ these are pseudo colors or false colors. The actual image is collected using infrared. So you see, here is the image from infrared, but here is the image from using false colors. It's interpreted and clear to human eye. Astronomers use light or electromagnetic wave to measure distance of astronomical objects. Astronomers ላይትን ይጠቀማሉ ምንም ሜዥር ለማድረግ አስትሮኖሚካል ኦብጀክቶች መካከል ያለን ዲስታንስ ሜዥር ለማድረግ። For more distant objects, we can measure the distance by using brightness of object. ኦብጀክቶቹን ብራይትነስ በመጠቀም ነው ዲስታንስን ምን የምናደርገው ሜዥር የምናደርገው። ሶ ክሎዘር ሲሆኑ ምን አይነት ብራይትነስ አላቸው፣ ፋርዘር አዌይ ፍሮም አስ ሲሆኑ ምን አይነት ብራይትነስ አላቸው የሚለውን ከለር ሪዞሉሽን በመውሰድ ነው የምንረዳው። So measuring the apparent brightness of an object enable us to calculate the approximate distance, and this law is known as inverse square law of apparent brightness, and it is explained like apparent brightness is proportional to the truth brightness over distance square. The truth brightness is also known as luminosity. The truth brightness, the actual brightness, is known as luminosity. Astronomers use very large units like parsec, light year, astronomical unit, or AU as an alternate astronomical distance measuring units. Okay, so these are the different units, but light year is the most common unit of astronomical distance. See, parsec is actually the largest one. One parsec is like 3.2 light year. And astronomical unit means AU, the distance, the average or mean distance between Earth and Sun is like 150 million kilometers. 1 light year is the distance covered by light traveling with its speed in vacuum for 1 year. So what will be that distance? The distance covered by light traveling for a year. Let's calculate that. What is the distance that light can travel in 1 year in kilometer? We know that distance S can be measured as velocity times t. This is the concept of physics from your kinematics. And c is the speed of light in vacuum, which is 3 times 10 to the power of 8 meter per second. But here, let's make it in kilometer, 3 times 10 to the power of 5 kilometer per second. And to find the amount of time, 1 year, into second, we have to convert this. So this is approximately 31,536,000 seconds, which is in 1 year. When you multiply these two, we can find that 1 light year is actually 9.46 times 10 to the power of 12 kilometer, which is 9.46 trillion kilometer. So this is it. Light traveled for 1 year with the speed of light to reach about 9.46 trillion kilometers. So astronomical bodies which are very, very far apart to each other, those distances can be measured using light year. Now let's try to solve one example based on astronomical distance. And the example is, there is a so-called Gliese 876, a red dwarf star, which is found nearly about 1.42 times 10 to the power of 14 kilometers away from our solar system. Here we have the red dwarf, Gliese 876, which is far away from our solar system sun. and it is about 1.42 times to the power 14 kilometers away from our solar system. Now the question is, what is this astronomical distance in light year? The choices are A 10, B 4.7, C 15.0, D 17.4. Now let's try to solve it together. What are the given variables? The given and required variables are the distance between the Gliese 876 red dwarf star and our solar system is 1.42 times 10 to the power 14 kilometers. Our question is to convert this astronomical distance in kilometer towards the astronomical distance in light year. And the solution will be, we know that 1 light year is 9.46 times 10 to the power of 12 or trillion kilometer. So what will be the same distance, which is 1.42 times 10 to the power 14 kilometer in light year? It's an easy calculation. ቀላል የሆነ calculation ነው። እሱ ምን ማድረግ ነው? ክሪስ ክሮስ ማድረግ ብቻ ነው የሚጠበቀው ከኛ። D times 9.4 times 10 to the power of 12 kilometer is equals to 1 light year times 1.42 times 10 to the power of 14 kilometer. So the astronomical distance D is equals to 1.42 times 10 to the power of 14 kilometer times 1 light year over 9.46 times 10 to the power of 12 kilometer. Kilometer will be cancelled by kilometer, 10 to the power of 12 will be cancelled by 10 to the power of 12, and here 10 to the power of 2 is left. 1.42 times 10 to the power of 2 will give us 142, divided by 9.46 will give us approximately, it is 15.001 light year. So our correct answer will be choice C, which is 15.0. I hope በቀላሉ እንደሰራችሁ ታምናለሁ።